Hello friend, let's learn today how to become an engineering wizard by getting the concepts in the spotlight and getting the math out of the way. So today I'll be using this nice little program called Geogebra to solve a typical problem that pops up in all statics courses, I would venture to say. So this problem is a single particle 2D equilibrium problem. So in this case it's stated as follows. It can pop up in many ways, but this is the one I selected for this video. You have two ropes attached at a point with some geometry data. And at that point where the two ropes meet, you apply a force of 10 kilonewtons, and you want to know what the tension in both ropes is such that the system is in equilibrium. So how much force should rope 1 and rope 2 resist? So this is a static particle equilibrium problem, and in this case, the problem is find forces with the directions of rope 1 and rope 2 with unknown magnitudes. So you need to find the magnitudes such as that they cancel out this 10 kilonewton force. So I've set up GeoGebra here so that the image is here. I have a nice origin, and I've scaled everything so that it matches the geometry of the picture. So let's put the origin out of the way. So let's start by defining some interesting points. And the obvious points are the vertices of the triangle. And from this, we want to define a couple of things. So let's define this force, 10 kilonewton force over there. The way to do that in GeoGebra, we're going to define F, I'm in caps lock, F to be a vector. A vector receives a point as an input. We don't have a point defined, so we'll define it. 10 times the cosine of 30 degrees. Degree sign is down there, it's very handy, comma, minus 10 times the sine of 30 degrees, and we're done. So that defines the vector F, and if you can see that it's placed by default at the origin of the coordinate system. If I can put the origin back on. So we might want to make it easier for us, we can move it all the way to the, oops, I accidentally, okay, let's put that so that it begins at point B. So there we go. We have a force defined at B that has the properties that we want. A 10 kilonewton magnitude and with the direction that we selected. Okay, good. So now what do we want? We want to define forces of unknown magnitude with the directions that of rope 1 and rope 2. So we're going to start off by specifying a unit vector. So we're going to call N1 a unit vector that describes the direction of rope 1 from B to A. So there's a command called unit vector. We can pick it here, and it takes an object and it turns it into a unit vector. So we want a unit vector from B to A. That would be the position of A minus B. There we go. And we'll specify another one to go from B to C. So unit vector and C minus B, and there's N2. Let's make these two green, which is the international color for unit vectors, and let's make them have their position start at exactly point B so that it makes sense and it's on top of our drawing. Now that we're starting to we have the geometry down, so let's make this picture a bit opaque so it gets out of the way. I'll still leave a little bit so that we can see it. Okay, so now what? So let's define some other things. So that we want to find the magnitude of force by the cable of rope 1. Let's just think that maybe that magnitude of the tension is going to be called T1, and let's just for now say it's 10 kilonewtons. And the second cable is going to have 8 kilonewton tension. We're just guessing at this point. But from that, I can define the tension vectors at B to be the scalars that we just defined times the unit vectors that we defined previously. So that's T1, and T2 is going to be equal to T2 times N2. So there I have two vectors which have the directions that I want. Let's just make them nice blue vectors. and again place their origin at the point of interest B. There we go. Okay, so now what? We have, so that's the problem. I'm going to erase the unit vectors for now. This is T1, T2. I'm also going to get points A and B out of the way, sorry, A and C out of the way. So here's the statement of the problem. I need to find the length of T1 and the length of T2 such that the sum of all these three vectors cancel out. So let's compute the resultant force to be equal to T1 plus T2 plus the vector F. Okay, so that's R over here. It interpreted as a point. So let's reinterpret that as a vector. We'll do that by actually saying vector here. Sorry, I'll redefine it. So let's say R is equal to a vector. The reason it did that is because GeoGebra actually interprets variables that you name with an uppercase as points and lowercase as vectors. So if I go R equals T1 plus T2 plus F, it's actually a vector. So let's just use that functionality. That's the resultant force vector. What's the color of resultant force vector? So everybody would agree that this resultant force vector would be this brownish color, I think. Yeah, or let's make it orange. Okay, so that's our resultant force vector. It's the addition of T1 plus T2 plus T3. The only thing I'm missing here is let's make it start at point B. So there we go. Okay, that's all nice. But we can see they don't add up to 0. So we can play around with the magnitudes of T1 and T2 so that we get it as close to 0 as we can. So I think I've canceled the T2 component there. And yeah, we can get manually very close, 9.8. T2 is almost 0, but I suspect that not quite. Okay, so how do we go about solving this problem and knowing exactly what T1 and T2 are? The mathematical statement of this problem is as follows. Find T1 times N1 plus T2 times N2 such that if you add F to it, that equals to 0. So N1 and N2 are fixed vectors. So let's evaluate to see what that equation looks like in matrix form. Here we go. We see that these values don't change, and these values are unknowns. And if I add F onto that, I should get a 0 here. So if I try to get close to 0, you can see that only the magnitudes are changing and the direction of the vectors are not. Okay, so there it's pretty close to 0, about 10 and 0.2. The way to write down that problem in math is as follows. So you put the N1 and N2 vectors in the columns of a matrix times a column vector that has T1 and T2. That has to equal to, with a minus sign there, which I forgot, the x component and y component of the force that you want. Okay, so that's the statement. So we need to invert a matrix. So let's start by forming the system of equations. So in GeoGebra, the way you write matrices is as a list of lists. So if I want to write a list or a matrix with 1, 2, 3, 4, that's how I write it. So I need a matrix that has the x components at the first row of N1 and N2 and the y components in the second row for N1 and N2. So I'm going to write M to be equal to first row x component. To get the x component of a vector, you can use the x function. So I give it N1. Did I write that correctly? N1, there we go. X component of N2. And let's go to the next row. Here we go. Y component of N1. And the y component of N2. So there we go. That's our matrix M. And then I'm going to compute a vector T1 and T2. So let's call that our solution vector. T is going to be equal to the inverse. So that's, we're going to call the invert function on the matrix M, and multiply that by the vector minus f. There we go. We get a point t over here. Remember that this this t contains the solution, so we're just not going to interpret it as a point. We're going to interpret those as the scalars that have to accompany t1 and t2. So let's now define t1 solution to be, and here you can see that we had what we had suspected before. So before we had about 10 at about -2. Our solution is minus 0.19 in the y component, about 10 in the other one. So we were pretty close, but not exact. So we're going to define the t1 solution as the first component, or the x component of that vector, x component of vector t times n1, here we go. And the t2 solution vector is going to be equal to the y component, or the second component of that solution vector, times vector n2. And there we go, that's our solution. Let's make these appropriate colors. So make them gray and place them at B, both of them. There we go. T1s, you can't see really T2s because it's a rather small vector. There you go. But once you get the resultant force for the solution, which would be T1 would be equal to T1s plus T2s, you'll see that leads, oops, and plus F, F like this, you'll see that leads to the vector 0. So we've solved the single particle equilibrium problem that we set out to solve. Now you can grab all of this stuff I just did and wrap that into a nice little tool that will help you solve any problem that you want. To define this tool, we'll start with a clean slate, and we'll repeat the process in a more abstract way. So we'll define 3 points, just like that, and the unit vectors pointing between them. So start with vector from start point A to A plus the unit vector that goes from C to A. So there's our vector u, and we defined another vector that starts from A and points all the way up to A plus unit vector B A. So V points from A to B, U points from A to C. The order doesn't really matter. Let's define a force. So a force is going to be F defined as a vector at A, and A plus some other point. So let's do 1, 1. This will be our red vector, and these are going to be our 2 green basis vectors. Just like that. Now, next step, we define the system matrix. As before, we're using the braces. So x of vector u, x of vector v. It doesn't really matter what you call these when you're creating the tool, because it's going to create a general tool. X of, y of u, y of v. So there we have it. That's our matrix. And then we invert the system. So t equals invert m, multiply that by the vector minus f, like so. And we get t, and final step, we're going to create a vector t1, which is the first component of t. So we'll use the x function again. We'll multiply that one by u, and t2 is going to be equal to the y component of t multiplied by v. And let's just really quick check that that sums up to 0. So t1 plus t2 plus f should give us the vector 0, 0. So with that, we now go to the create a new tool menu. So we go to tools, create new tool, and we select what our output we want. So we want T1 and T2. We want the final vectors to be our output, and our input objects are going to be not the points, so I'm going to get rid of those, but they're going to be in this order: the u vector, the v vector, and finally the force. Let's call this particle equilibrium and store it like so. So we can start again. I'll select all objects, erase everything, and start over. So point A, B, and C, and define some vectors. So I'll define the unit vector, vector starting from A, and finally the force. Let's call this. There's one vector, and the next one is next one. So we can start again. I'll select all objects, erase everything, and start. Define a force, okay, and define some vectors. So I'll define the unit vector, Now, instead of doing the previous process, we'll use the tool. So I'll use this tool. This is our u vector, v vector, f vector, and as you can see, it gives you the resultant vectors as expected. And the naming convention here is automatic, so you don't really know what names you're going to get. There's some ways to get a control, but in this case, I get T and then I get A. Okay, so if this all worked, then T plus A plus F should give us 0, and that's exactly what we have. So with this tool in mind, next video I'm going to do is how to use this tool to quickly solve truss problems in statics. Until next time.